Okay guys, here we are in chapter 23. This is our last major chapter that we'll have, and it's entitled Carbonyl Condensation Reactions. Now, the last experiment that we were scheduled to do in lab was dealing with this kind of thing. It's unfortunate that we were not able to do that experiment. But I'll talk about those kinds of things in this particular chapter. And so let me kind of give you an introduction here, just so you can have a feel for what we're talking about. So far we've looked quite a bit at ketones and aldehydes. We've also seen esters, so on and so forth. But one of the interesting things about them is that both aldehydes and ketones, esters, so on and so forth, they can behave as electrophiles, or they can behave as nucleophiles. Just depends largely on the sets of conditions that we'll be looking at. Now, for the case of a carbonyl compound behaving as an electrophile, that would be this type, where a nucleophile attacks at the sp2 center. And you've seen several examples of that. One example would be the Grignard reaction. Another reaction would be the reduction reactions with sodium borohydride, lithium aluminum hydride, diacetyl aluminum hydride, cyanohydrin formation, ketal formation. There's even others, amines, so on and so forth. And that was what we were looking at in previous chapters. But we also learned that if you form an enolate, that carbonyl compounds can actually behave as nucleophiles. So in this chapter we're going to see how these work interchangeably. Now let me go down the page with you and talk about what this chapter actually entails. The first reaction we're going to look at is called the aldol reaction. I'll tell you how that works and where the name comes from. And if you can understand this reaction, then you can really understand the remainder of the chapter. It's all based on that. Then we're going to talk about dehydration of aldol intermediates. In other words, how we go from the aldol to an enone. Then we're going to look at these kind of reactions involving esters, one called the Claisen reaction, one called the mixed Claisen. We'll also look at one where we form a ring, and we'll look at the so-called Michael reaction. And there's two other really important ones in the chapter. One's called the Stork-enamine, and one's called the Robinson annulation. But we just don't have the time to cover those last two. So let me go ahead and begin with you in terms of the chemistry by taking a look at page 176. The title of the first section is called Carbonyl Condensations, okay, and the aldol reaction. Now the word condensation basically means that you're going to conjoin two species. They're going to condense, they're going to come together, and they're going to exclude by eliminating a small molecule such as water or methanol or something like that. But those are called condensation reactions. Now the focal point of this first part of the chapter deals with the aldol reaction. Now the reason it's called the aldol reaction is because we're going to produce a compound called aldol. Now this is aldol itself, but there's other examples of aldols. Now, how would that work? Well, here's how it works. We're going to take two identical compounds, okay? See that? And in this case we have acetaldehyde. And basically what we're going to do is we're going to join this carbon to that carbon. In other words, this is going to behave as a nucleophile. This is going to behave as an electrophile. Okay? Now they don't just do that spontaneously. You have to have a catalyst present. In this case, it's going to be a base. Interestingly, you can actually do this reaction with acid as well. And like I mentioned a moment ago, this is a condensation reaction because they're going to exclude a small molecule, and oftentimes that's going to be something like water. So if you look real closely over here, you'll take notice that we formed a new bond there. You say, what is that new bond? That new bond was between an alpha carbon, okay, of acetaldehyde, and a carbonyl carbon of acetaldehyde. Now the reason it's called an aldol is because you'll notice the product has an alcohol, an OH bonded to an sp3 carbon, and it has an aldehyde. So we put those terms together, ald and ol, we get aldol. Now this doesn't have to be an aldehyde, it can actually be a ketone, and we'll see later too that it can be an ester. But this is the generic term for the simplest aldol reaction there is. Now let me go on and mention a few more things because this will matter as we go through this material. First of all, aldol reactions are typically base catalyzed, that's what we're showing here, but they can be catalyzed by acid. I'll show you an example of that too. The alpha carbon must possess at least one hydrogen atom. Okay, and you can see we have 3 there. And the yields are favored if the alpha carbon is not hindered. In other words, if you got a lot of bulky groups around here, it's going to be hard for this to behave as a nucleophile. And as I also said, ketones will undergo aldol reactions as well. And then once we kind of develop this theory, we're going to talk about how aldol products, okay, this is an aldol product, is prone to dehydration. And then ultimately that's going to render an enone. So this is a very intricate process. It's one of the best ways to make carbon-carbon bonds, and then as you'll see, carbon-carbon double bonds. Now taking into consideration this reaction here, let's talk about how that mechanism would actually ensue. In other words, I have here in the middle of page 176 a mechanism to explain this reaction. Now we said that we need a base to catalyze this, so here I'm showing hydroxide. And again, this only needs to be a catalytic quantity. So the other requirements, you have to have at least one hydrogen, right, on an alpha carbon. As you can see, we have that. Okay, we have 3. So what's going to happen is that the base is going to pick up a proton from the alpha carbon. Okay. Now the pKa of acetaldehyde is about 16.7. So it's a very weak acid. Now, once we deprotonate acetaldehyde, what do we get? We get an enolate. Now the enolate I'm showing you has the carbon with the negative charge, but we could draw this in its resonance form where the negative charge would be on the oxygen. Which resonance stabilized? And here's water that was produced as a result of the hydroxide picking up that mildly acidic proton. Now recall that the pK of water, okay, it's about 15.7. So we definitely have an equilibrium here, all right? In other words, it's actually just slightly favored to the left. So we've established an equilibrium. Now go back up here. We said that we have 2 equivalents of acetaldehyde. Okay? You can think of this as 2 molecules or 2 moles, however you want to think of it. And here's our second equivalent. Here was the first. This is our first molecule. I'm going to call it equivalent. And here's our second equivalent. All right? So we said a while ago that enolates behave as nucleophiles. That's exactly what's going to happen here. We're going to have this carbon act as a nucleophile towards a carbonyl. And when it does that, we establish a new bond. Okay? So you can see the new bond right there that I'm highlighting. So this is an alkoxide. Now recall that hydroxide was catalytic. So we can show that catalyst being restored by the alkoxide picking up a proton from the weakly acidic water molecule, and therefore, what do we end up with? We get our aldol. So this is aldol. Okay, that's how it forms. And so if you can understand this mechanism, you can understand the entire chapter. But bear in mind also that when the alkoxide picked up this proton, we got our catalyst back. So this can go back here and repeat the process over and again. Now, as we start to go through this and we get into more detail, we're going to see that most aldol reactions, not all of them, irrespective of the structure of the aldehyde or the ketone, follow this mechanism. So this is a good one to review. Now keep in mind you got to have at least one hydrogen here, okay, in order for this reaction to take place altogether. Let's flip over to page 177. If you look at the top of page 177, what I've asked you to do there is to predict the aldol products. Okay? So we don't want to go through the entire mechanism. Instead, we would just kind of like to be able to sketch it out. Okay? And that's what I want to show you here. Now, if you just think about this in the most basic of terms, what were we doing? Weren't we joining an alpha carbon to a carbonyl carbon? Isn't that what we're doing? We're just joining those? Yeah. But what did we also say happened? What was the fate of that carbonyl? That carbonyl becomes an alcohol, right? In other words, it's no longer going to be, once we go through the whole process, it's no longer going to be a carbonyl, it's going to be an OH group. So if you just keep that basic idea in mind, you'll get these right every time. So let's just do that. Let's just take this rudimentary approach to determining the structure of this compound, like I just said. So here we go. There's that first set of carbons, okay? There we can just go straight up like that. And what I'm going to do, I'll use a different color here so you can get a better appreciation for what's happening. Here's my new bond in green. You can tell that's green or not. And here's the rest of that molecule. Okay? And then what did we say the fate of this carbonyl was? We said it becomes an OH. Yeah. So guess what? There's your product. That's the aldol product you would get by combining propanol together with another propanol molecule. So this is an example whereby we're combining aldehydes, hence propanol, to form an aldol. This is your answer. This is your answer. Now, I also indicated that you could do this with ketones. Okay. So here we have cyclopentanone, and let's follow that same logic that we did just a few seconds ago. Let's just go ahead and find an alpha carbon. We have 1, 2, 3, 4 alpha carbons. I'm just going to choose this one, and I'm going to join it from here to that carbonyl. Being mindful that on the acceptor side, that particular carbonyl is going to become what? It's going to become an OH. So we don't have to work out the whole mechanism for these. We just have to be cognizant of what's going on. So let's go ahead and sketch this one. I start by sketching the cyclopentanone on the left. Okay, there it is. Let me go ahead and make my new bond here in green. You can see that. And now let me draw another 5-membered ring. And let's just be mindful that this becomes an OH. Okay? So this is your aldol product. Now you might notice there's something all of these have in common. Whether you go back to page 176 or now, let's look at what they have in common. I'm just going to start here at the carbonyl, okay? And I'm going to move through this bond. Okay, there's a new bond, and there's the OH. See that? We have that in all of these. We have that basic framework in all of these. You have an OH, carbon, carbon, carbonyl. Right? OH, carbon, carbon, carbonyl. We have that every time we generate our aldol products. So that's something to keep in mind as we move forward as well. So the aldol reaction is a very important way for making carbon-carbon bonds. And we're going to see how more important it is, more so than just what we described here in a few seconds. So there's a chapter in your book I'd like you to just read for background. It's related to what we're talking about here. But what we're going to do is we're going to continue with this logic here and try to understand what's meant by the term dehydration of aldol products. In other words, these are going to be, if you leave them in the flask long enough, or if you add extra base, they're going to dehydrate. And the driving force behind that is that they're going to become enones. Okay? So, let's read what I have written here so that you can understand what's going on. Most aldol intermediates are prone to dehydration. In other words, they're going to lose water. The final products in these types of reactions are known as what? Enones. Okay, so you can see I have a generic enone right here. Enone products are obtained in many cases by the use of excess base and or heating. Okay? So the lab that we were supposed to do, the dibenzyl acetone, you were going to use a large excess of base so that you could force the aldol intermediate to dehydrate to become an enone. But another reason they're favored is because they're conjugated. As you learned earlier, conjugation enhances the stability. So hence that's another reason that enones are favored. Okay. Now, let's think about what the enone backbone is as a reminder, and then let's go over how these aldols can become enones. So an enone is characterized also by a carbonyl, a bond here, carbon-carbon double bond. Okay? Hence, ene like an alkene, one like a ketone. It's an enone. And these species are very stable. Why? Because they're conjugated. Remember that? They're conjugated. And that's the driving force for their formation. So each of these could do that. And I'll show you how that works. So let's take back to the first reaction we had on page 175, where we talked about how acetaldehyde could be converted into aldol. Okay? But let's just suppose now you let the reaction stir longer and longer, or you had extra base. Okay? So how could that influence this? What's going on here? Well, let's remind ourselves what this carbon was. Wasn't this the alpha carbon? And what do we say about protons on alpha carbons? Aren't they mildly acidic? Okay. So what can happen if you have bases around, you can pick up that proton, either one of these. This pair of electrons can collapse in between the alpha carbon and the adjacent carbon, and then you have the elimination of hydroxide to get your catalyst back. Okay. Now, look what you get. You have an enone. Now, technically it's an enal because it's an aldehyde, but it's still referred to as an enone. And have y'all seen this reaction before? You sure have. Folks, this is an E2 reaction. So the driving force is highly favored to the right here. Why? Because now it's conjugated, okay? That's the driving force behind this particular process. So keep that in mind. Now, let's go to page 178 and talk briefly about what we've just said. Now when you form enones, realize you're forming a carbon-carbon double bond. So typically it's the trans diastereomer that predominates. And the dehydration can proceed by way of E1 or E2. Just depends on the sterics around that alpha carbon. The leaving group is abstracted, and the abstracted alpha proton will possess an anti-periplanar relationship for optical elimination, and that's something you had in times past. And the dehydration may also be catalyzed by acid. So let's take a look at that, how that would work. So in sample problem 22.02, I showed you how you could form an enone from basic conditions. Here we have it under acidic conditions, right? So here we're going to have an acid. You have an aldol. Here it is, the same aldol we've seen. And the OH can pick up a proton, right? Which now you have what? You got a really good leaving group. So since the hydronium ion was a catalyst, we could get that catalyst back. So we pick up a proton again from an alpha carbon. This pair of electrons collapses between alpha and the adjacent carbon, and water departs. And what did you get? You get the same product we had on the bottom of page 177. And again, the driving force here is that you've got a conjugated species. Okay? So you can actually dehydrate aldols under acidic conditions just like you can under basic conditions. This reaction probably is more facile because water is a better leaving group than is hydroxide. Now, a while ago I asked you to predict an aldol product, right, without going through the mechanism. We're going to do the same thing predicting the enone product without going through the mechanism. Okay? We're just going to go directly to the product. And the way I've shown you is using lasso chemistry. And what I mean by that is to locate your alpha carbon. Okay? In this case, you have to have at least 2 hydrogens of one molecule, and locate the carbonyl carbon of the other molecule. Draw a circle or a lasso around them. And then what you're going to do is you're going to join. Okay? Let me just draw some arrows in here. You're going to join this carbon to that carbon with a double bond. Let me just write DB for double bond. Okay? And then automatically, by virtue of you doing that, you've come up with your enone product. So if anybody ever asks you, what's the enone you get from this particular reaction? This is the simplest way to do it. So let's try some of that. Let's go to page 179. Question here is, what enone products would you expect from the aldol condensation fine compounds? Okay, and I have cyclopentanone here, and I've got 3-methylbutanol there, so a ketone as well as an aldehyde. Well, let's use what we just talked about, okay, on the bottom of page 178, and that is, let's locate our alpha carbon. I'm going to put the letter alpha there, and I'm going to place those 2 hydrogens on it. Now, what do we do now? Let's go ahead and draw a circle, or I've been calling that a lasso, around the elements that constitute water. Now, what are you supposed to do? You're going to join this alpha carbon to that carbonyl carbon using a double bond. So here's that cyclopentanone ring system. Okay. And we put a double bond in there, and you got it. That's it. So it works every time. Let's try it with an aldehyde. So it's incumbent upon you to recognize the alpha carbon. These are identical compounds, right? So the base is going to form an enolate here. That enolate is going to attack carbonyl, and then all these other steps occur that we've described in the mechanism. And eventually we're going to go all the way to our enone. So there are two hydrogens explicitly written on the alpha carbon. All we got to do, okay, is draw a circle around those, or a lasso, they've been calling it. Okay, there's your lasso. And you're going to join this carbon to that carbon with the double bond. Okay? Alright, so let's give that a whirl. Alright, so here I am. I'm going to draw it. This is going to be a carbon-carbon double bond now. Alright. There it is. And there we have it. Right? There we have it. That's how you do this kind of problem. So we're directly from these aldehydes and ketones to the enone product. So these are both enones. Now, some people call that an enal because it's an aldehyde, but you can call it an enone. And what do we say they all have in common? They've got a carbonyl. There's your carbonyl. Single bond, double bond, double bond. They all have what I highlighted in yellow in common. And that's what makes them enones. So here's an enone from a ketone, here's an enone from an aldehyde. Now if you really grasp this next problem ought to be pretty simple to learn. As you know, one of the primary tasks of organic chemists is to figure out structures to synthesize things. Over here on the right you're looking at the species, and you don't have to worry about naming these, okay? You're probably glad about that. But what if it was your job to synthesize that? I mean, in the lab, you need to make that. First thing you do is you say, well, this is an enone, right? There's a carbonyl ketone part. I know how to do that. If we created a double bond between alpha and the carbonyl, then why don't I just draw a line whereby I split those two? Okay? So now I have two fragments that I can sketch. Let's just sketch everything you see here minus that entire double bond. Okay? Alright. So on the left-hand side, this is what we have. I'm going to draw everything I see there minus the entire double bond. Okay, there's half of it. Now let me sketch the other half, so to speak. So if you've gotten that far, you got it made. Now what's left to do? Look up here. Wouldn't that be a good place to put a carbonyl? And would this be also an equally good place here to place two more hydrogens? Okay. And we put a plus sign in between. Okay. So I know that if I have these compounds and I add a base, the right kind of base, I can produce that. And what do you notice about these compounds? They're actually identical, right? Yeah, this one I've shown all the hydrogens, okay? Here I've shown it as a condensed methyl group, but these are actually identical, and this is your good friend, acetophenone. Okay? So sometimes you'll see a chemist just put a 2 in front of this, okay, because there's 2 of them, and then show you that. But we don't really have to worry too much about balancing our reactions. So as a double check, let me just find out what happened here. I'm going to put a lasso around the elements that constitute water, because after all, water is a byproduct. If we want to show that over here, we can, just as a reminder. And yeah, we joined that carbon to that carbon with a double bond. There's that double bond. All right. Now, so that we don't get too far ahead of ourselves, because we don't want to learn tricks or anything like that, but we really want to know the chemistry behind all this. Didn't we say that was the enone? Okay, but don't we also have an intermediate? In other words, it's got to proceed through a covalent intermediate before it gets to there. Let's not lose track of that, okay? So let's draw the aldol intermediate that we would get. And let me show you a simple way to do that. You say, well, you already showed us how to do that. Let me just remind you. Here's what I'm going to do. I'm going to go ahead and sketch this structure here. Okay. Much the way I see it. And then we need to finish this up. And didn't we say that water is a byproduct? And while it's not required that you place it there, it kind of reminds us that, hey, one of these needs a hydrogen, and the other needs an OH. Okay? I can put that OH just about anywhere I want to. So this would be the aldol intermediate. So when you do the reaction in the lab, these two would condense. They come together to give you this intermediate. Now you either have extra base or you're stirring it for a long time and or you're heating it, but over time this becomes that. Okay? So this is how you make these really complex looking enones using aldol chemistry. Alright, now there is a, said using aldol reaction synthesis, read for background. Kind of gives you an idea of how we can actually use these things in a broader view. Well, is it that simple? Not always as simple as we may think at first. There is something called a mixed aldol. Okay? And let me describe what that is. And I'm going to show you how you can take different aldehydes under ketones, but yet get one product. Alright, so here's our scenario. Suppose one conducted an aldol reaction upon a mixture of what? Two different aldehydes. Okay, two different ones. Well, theoretically, one would obtain 4 different aldol intermediates. And that's not good, because these are all going to be just about impossible to separate from one another. Okay, and the highest yield you can anticipate would be like what, 25%. So this is bad chemistry, but it makes the case. Okay, because you see, acetaldehyde could react with itself. Okay, propanol can react with itself. Okay. Propanol can act as an electrophile. This can act as a nucleophile. This can act as a nucleophile. This can act as an electrophile. So what did you just say? What I basically said is this is bad. Okay? In other words, if you try to take 2 different aldehydes, you're going to get, in this case, 4 different products. Alright, so that's not good chemistry. But can you do a mixed aldol? And the answer is you can. But there's certain parameters have to exist. I'm just going to show you 2 of them. In the first case, we have a mixed aldol with one partner containing no alpha hydrogens. Okay? So let me just kind of give you a background for what's going on. So here we have what we call a donor, and that's the one with alpha hydrogens. And here we have one called the acceptor. That's the one with no alpha hydrogens. So let me make sure I underline that with you. There's no alpha hydrogens here. Now a donor, okay, is nothing more than a nucleophile, because it's going to become an enolate when you remove one of these protons, be negatively charged, and it'll attack there. So as you know, the acceptor is what? An electrophile. So in the lab, you just don't put these together and expect them to react that way, but you have to follow the procedure very carefully so that you end up having this as the donor and this is the acceptor. Okay? So as you can tell, though, just like we've been saying, we make an enone, okay, and you can tell that we have an enone by reacting those two together in that form. So this is one way of doing a mixed aldol. Okay? Mixed because these are two different carbonyl compounds, yet they only give us one product. Now you could make the case that you get a mixture of cis and trans here, but you don't get things like that. Now the other example is a mixed aldol with one of the partners containing more acidic hydrogens. Okay? Alright. Now, let's find out what's going on here. Here we have our donor. This is the one that has alpha hydrogens. There they are. And here's our acceptor. So wait a minute. The acceptor has alpha hydrogens too. But the pKa's are very different. This is our good friend ethyl acetoacetate. Okay? That's the one when we were discussing the acetoacetic ester synthesis back in chapter 19. And the protons here have a pK of about 13 because they're between two electron withdrawing groups. Okay? Whereas the cyclohexanone, the protons have a pK of about 19. So if you take 10 to the 19 minus the 13, you're going to get 10 to the 6th power, which is a million. So these are a million times more acidic than are those. So if you're a base, who are you going to go after? You're going to go after that proton. This is going to become an enolate, and therefore it will be what? The nucleophile. So the one with the more acidic protons becomes the nucleophile. And obviously this will end up being, okay, the electrophile. And if we follow the logic that we had just a few moments ago, let's circle the elements that constitute water, draw a lasso around them, join this carbon to that carbon with a double bond. There you have it. So yeah, two different carbonyl containing species, yet we get one product. So this is called mixed aldol. Let's go a little bit further. Okay, I'm on page 181. Describe how you would prepare the following enones using a mixed aldol. Okay, so we're going to look at this as an enone. So how can I do that? Folks, this is really simple. Since you're forming carbon-carbon double bond, okay, you may as well separate it, the carbon-carbon double bond. And then draw each of those species as if the double bond was completely gone, and then fill in the nuclei that belong there. Okay, so I'm looking at the left-hand half of the molecule, so to speak. Right. A little bit neater here. And there it is. Okay. And here's the so-called right-hand part of the molecule. And then all that's left now is to fill in the remaining nuclei. Mm-hmm. So they're both carbonyl containing species, so this one's going to need to be a carbonyl. Right? And of course this needs to be, in this case, fill in your two hydrogens, the ketone part. Let me put a plus sign in between these two. Probably should have a little more space to make that a little neater. So here, the donor is what? Acetophenone. And the acceptor is what? Benzaldehyde. See? And there you have it. Using mixed aldol chemistry. Let's do one more. Like I said, break it there, but carbon-carbon double bond. Sketch your two portions of the molecule. And since either one's up here and one's down there, I'm just going to do it the same way. Kind of sketch those together like that. So I'm going to draw everything I see there minus the entire carbon-carbon double bond. And then what we're going to do, once we've finished that part, we're going to come back and fill in the so-called missing atoms, which is always 2 hydrogens and 1 oxygen. These are hydrogens, this is a hydrogen. So help me finish this one up. What do I need to put here? Yeah. This is where I place the 2 hydrogens, okay? Between the 2 electron withdrawing groups. And here's where the carbonyl goes. And let me put a plus sign in between those. So if you follow that logic, this carbon would join this carbon with a double bond, okay? And that's why this is called a mixed aldol. Okay, I think this is a good place to stop. And we'll come back here in a little bit and finish this one up. See you later.